we want to take a carboxylic acid up to an amide or an acyl chloride, something far up the reactivity ladder, we really need to activate it. And what that really means is converting the OH group in the carboxylic acid into a good leaving group. To do this, we make use of some electrophilic reagent. And I'm showing two examples here. We'll look at more examples in more detail when we talk about peptide synthesis in discussions of proteins, because this is the essence of peptide synthesis, converting a carboxylic acid into a good electrophile so that an amine can attack it and we can form an amide or a peptide bond. The first reagent listed here is thionyl chloride, and thionyl chloride is a great reagent for chlorinations. We've actually seen it already in the context of converting alcohols into alkyl chlorides, and so it makes sense, at least from a general point of view, that the treatment of a carboxylic acid, which contains a hydroxyl group within it, with SOCl2, results in the replacement of the OH group by a chloride to make an acyl chloride. And the nice thing about this is once we've got the acyl chloride in hand from the carboxylic acid, we can use pretty much any nucleophile here. Could be neutral or anionic, any kind of HNu or anionic nucleophile to produce really any carboxylic acid derivative we want. So it's a discrete synthetic step, the synthesis and isolation of the acyl chloride, but once we've got that in hand, that can be converted into pretty much any carboxylic acid derivative. Particularly within the peptide context, a reagent that's been used with success is Dicyclohexylcarbodiimide, or DCC. And DCC has a structure that's reminiscent of carbon dioxide, with two carbon-nitrogen bonds associated with a common central carbon. This is a great electrophile, and the essence of this reaction involves the carboxyl oxygen, the carbonyl oxygen, as a decent nucleophile, and the carbon, the central carbon within DCC, as an electrophile. The group that this installs contains a new oxygen-carbon bond and has a structure like this. This may not look like much very special. All we've done is added the carboxylic acid across some of the carbon-nitrogen pi bonds. However, this entire fragment here that I'm highlighting in blue has the potential to act as a leaving group. You can imagine if we put negative charge on this oxygen, that's heavily resonance stabilized via delocalization on both of these nitrogens. And so under the right conditions, we can get what I'm highlighting in blue to act as a leaving group. And of course, that's really the idea of both of these reactions, replacing the OH group with something that has the potential to act as a leaving group or nucleofuge. DCC is generally used for amide-forming reactions. And so, for example, we can take an amine, say a primary amine, H2NR, and end up with an amide product. I won't draw it out explicitly, and we'll see many more examples when we talk about peptide synthesis, but this is the basic idea behind peptide synthesis. Change OH into a good leaving group, and then hit with a nucleophile.